Okay, good afternoon, one and all the participants. It's a last session of the FDP, and we have the eminent speaker with us, Dr. DIptendu Sinha Roy. He is working as associate professor in Department of Computer Science and Engineering, National Institute of Technology, Meghalaya, Shillong. He completed his PhD in engineering from Birla Institute of Technology, Misra. MTech is also in the computer science, Birla Institute of Technology, Misra, and also sir completed BTech with specialization electronics and telecommunication engineering from Kalyani University, Kolkata. Sir is also guiding number of research projects under the DST SCRB and Ministry of Home Affairs, and previously, sir is working as in National Institute of Science and Technology, Barampur, as associate professor, and also in prior of this, sir is also work as senior lecturer in the same institute, NIT Barampur, NIST Barampur, and also before that, like from 2005 to 2007, from the same institute, National Institute of Science and Technology, Barampur. And sir published number of research paper in the reputed international journal and conferences. And sir is also take the responsibility towards institute administration at NIT. Sir is also have the responsibilities from 2017 to 2019 as a head of department computer science and engineering in NIT, and also faculty in charge in computer center from 2018 to 2020, and also Senate nominated member of Board of Governance 2017 to 2019, and also the convener Campus Network Community 2018 to till date. And the area of interest research is like grid, cloud, and distributed system, machine learning, application of soft and evolutionary computing data, analytics in a smart and grid domain, and software reliability. So we are ready to welcome you, sir. It's our pleasure to because many times I sent the mail and also send the request to the sir to at least give us 1 hour time to deliver the lectures to our all the participants. So we are ready to welcome you, sir, and we are ready to listen to you actually.
Thank you.
Thank you, sir, for accepting our request.
Yeah, it's welcome.
Now it's over to you, sir.
Thank you. So, thank you very much, Professor Agarwal, for the kind introduction. I deem it a great pleasure actually, and it's a great opportunity for me and to share whatever I have been doing over the past 15-20 years of my professional career. To share my knowledge, share whatever experiences I have. So, this topic is very close to what I have been doing actually. As Professor Agarwal introduced that my BTech degree was in communication, and then I did my master's with a specialization in networking, and finally my PhD. So, and I have been working in areas in cross-disciplinary areas from the beginning when I had been doing research. So, in fact, currently I am, although I'm from basically all my teaching and research experiences primarily have been in the domain of computer science. However, I have funded projects from ACRB, a core research grant with Power Grid. So primarily doing data-driven, data-driven investigations with Power Grid data. So the scope of this lecture is very, very huge. So it's not possible. I mean, I'll try to make it as generic as possible. Just I came to know that the audience somehow or the other is not necessarily from electrical department. So that is a relief as well as it's a challenge. So I'll see as we go along how things pan out. I'll try my best to share what I have done.
Sir, sorry to interrupt you, sir. Gopal here. Sir, a bit louder, sir, please. Your voice is
maybe
a little louder, sir. Your voice is you're audible, but little louder, sir. It's muted, sir, right now.
Okay, I think it got muted automatically. Now is it okay?
Yeah.
Because I think the
Yes, yes. Now it's okay, sir. Now it's okay.
and I'll not use the microphone. The microphone is a new one,
Okay.
so it might be an issue. So
Okay, okay. No issues, sir.
okay,
Now
thank
you
you.
just open your PPT, sir.
Yeah. So I would rather prefer that we have, because this topic is such a open topic, na, so we can keep on discussing on different aspects of it. Uh, I'll try my best. I will be rather pleased if you have any discussions on the different topics, right? So there have been different facets in which artificial intelligence has been applied to different aspects of the electric power grid. So that we'll discuss. I'll start out, try to generalize uh, the main principle, the main philosophy for applying AI to the electric power grid. Then we'll take up a few use cases to the extent time permits. And of course, I have to, as a matter of duty, I'm duty bound to tell what research I have been doing and with power grid. So it will just be a very brief, generic overview. I'm sure that will be able to generate a lot of interest based on that discussion. So because of bandwidth considerations, it's better um, that I switch off my video, because that might hamper. I'm doing it from home also. Fine. So
Okay, sir.
yeah. So we will start. So let me just have a time cap, because I have to finish by 5 o'clock. Okay, we have sufficient time, hopefully. So just very briefly, what my goal will be to, briefly introduce, as I told you, the main philosophy, why we are, the main challenge in a integrated power grid, and then we'll see like what have been the different use cases which have been popular at different points in time at different parts of the country, world, and then focus on a bit of the use cases which will be more relevant to a society like us, middle income group, lower income group countries, and to that extent how data analytics and machine learning can be employed for this. A few use cases, then of course I'll very briefly I'll show what work I have been involved in with smart grid, and then the new challenges which come along with it. Okay, particularly the integration of renewable energy of the grid and what challenges that brings. Okay, a few applications, and then finally what can be the potential challenges and how the future of the power market looks like. Right. So, lot to cover. In between, probably, because if I take the questions later, I don't think I'll be able to finish to my satisfaction. But then I'll try to, at some point in between, to have a pause and see if there are any questions. Okay, so as we know, the modern world actually depends on electricity. So not just for the luxury to use our devices and enjoy our free time, not even just for the convenience of having, facilities like lighting, heating, and cooling in the different buildings, but more importantly, because it's a very, very, very crucial resource, especially in urban areas, semi-urban areas, also of course in rural areas. That is not a bar, but why this crucial resource? This is so crucial because everything depends on it, starting from the public security, the safety, the healthcare facilities in a city particularly. These are primarily more developed in cities, so in that sense it is especially more relevant for much more it becomes much more crucial in cities. Okay, so this makes possible everything from emergency response to modern medical emergencies. Okay, and of course this that's why we call it a utility. So there are very few primary utilities that we are aware of. Okay, the utilities like power, gas, having running water in our. So similarly, having electricity is, that's why electricity is one of the primary utilities. But this has a peculiar challenge, as I told you right at the beginning, that I will be focusing on the prime requirement, why we need to have AI for a power grid. So that point I'll just drive home now. So unlike other utilities like water or other gas and all, so this electricity can actually not be stored. Okay, you can't store electricity. Of course, we can have batteries for to act as electricity storages, but then the volume of the huge, tremendous amount of energy that we expend, the electric energy that we expend every day, compared to that, actually the amount that we can store, I mean, that is actually very, very negligible, almost nothing that we can store. So in that sense, this electricity has to be produced, transmitted, and used very, very effectively. So there lies the challenge. Okay, so it requires very detailed sort of an infrastructure, very, very complicated infrastructure to build such a power grid. So that particular infrastructure which makes this possible, makes what possible? Electricity being produced at different corners of the country. Let us take the example of the Indian scenario. Okay, and then transmitted from all those. Usually they are at very remote places. To get them transmitted, I'm sure all of you must have seen the different electricity, those, not these distribution lines which runs across the different roads and so forth, but rather I'm sure that you must have seen those, particularly in rural areas, the huge those electricity poles, towering size. So they are actually ubiquitous, available everywhere. So this infrastructure which connects the generating units to the transmission facilities which actually are owned by Power Grid, and then through the different utility service providers, the distribution companies. Okay, so they make electricity reach our homes and our offices. So this connected nature of this makes it what we call this infrastructure, what we technically call as the electric power grid. So a very, very grand arrangement of things, and actually we take it for granted. Whenever we switch on a light or a fan, we actually don't understand the complexity which is involved in bringing this power to our homes from those remote places, okay, where it is actually generated. And don't forget the main challenge. The main challenge is, for such a huge system, the amount you generate has to be expended. So if you generate more, it's a wastage, it's a loss of economy, and you lose money on that. And also generation is more, so it creates a lot of instability to the entire system. And otherwise also it creates a problem, in the sense that if you generate less and you consume more, so the prime challenge in the entire scenario, electricity generation to transmission, and finally at the distribution and using the different loads, connecting the different loads to the power grid. So this involves actually a very, very complex network. Okay, that infrastructure, what we are calling as the electric power grid. So this makes it possible for us to draw power from that particular scene. So as such, it can be conceived as a very, very complex machine, single machine, not in terms of a single component, but you can think of the entire, at least for the Indian scenario, as the entire, from the lengths and breadths of the country, whatever infrastructure are there for electrical generation, power generation and transmission and distribution, everything as if it's a single machine. So that is the concept of grid. So which makes it possible is by the interconnection. So if we have isolated generation and transmission, so suppose you want to generate some power at your own backyard at your home, which powers your house. So if that particular generator goes down, you don't have power. So your system, your electricity that you can consume, that electricity will not be uninterrupted. It won't be reliable. So by the same logic, so suppose if you have, for a particular city, there is a nearby power generation field, so that whatever power plant or something, so that will not ensure uninterrupted service. So if we can connect all the different generators and the different loads, that makes the power entire grid a reliable one, and which technically is called the grid, which basically means interconnected system. So there are several challenges involved, electrically also, engineering wise also. We'll not go into the basic details, but let us remember this thing, that we have to, the goal of power engineers has to be to make this equation, the total demand has to meet the total supply. Okay, so it's a very, very complex system, as I've already mentioned. Complexity runs from at the generation end. Okay, so where there are generation stations, usually NTPC is the
biggest player in this market, Indian scenario. Okay, so then getting the power, I mean, if there are very complex techniques to putting into simplified terms. Usually they are transmitted at very high voltage and using very high frequency for minimizing losses and so forth. So we in India, we have a AC grid, unlike other countries like China and so forth, and it's in fact the largest interconnected network in the entire world. Okay, there are actually, US don't have a single grid like we have in India, that but even this the different regional load dispatch centers, then under this POSOCO they operate it. It's the single largest. US has many such grids. They are not synchronized as a, I mean, at the national level. And China also has, I mean, the total infrastructure is more than us, but it's not a synchronized single grid. They also have certain DC grids. Okay, anyway, I'm not going into the further details, but just to remember that at the generating end, before transmitting, the voltages have to be stepped up, and then at high frequency it is transmitted for minimizing the losses. And there are all these distribution, I mean, transmission lines, these huge poles which I have seen, which you have seen, at least 5-story, 10-story building tall. So those carry those high tension lines. I mean, okay, so then from there, actually, they are finally, when they reach the different substations, I mean, at the different cities and so forth, so they are stepped down and all. There are feeders, there are smaller transformers to step down the voltage. And finally, as per the, I mean, they are delivered as per the requirement of different industries or different residential purposes. Okay, so majority, these AC grids are advantageous in that sense. Okay, in India, actually, it's a 50 hertz uniform, synchronized, fully synchronized AC grid, which is not the case, as I told you, in like in China, or not the case in the US also, because they have multiple. It's not that it's a single grid. Okay, so very complicated operation. So now this brings new opportunities that we should not forget. Just a minute. Okay, new opportunities like it creates a market, because now we have different players. I mean, there is something technically we can discuss in there are any questions. So, I mean, what deregulation is and how the market players were broken down into different categories and so forth. Okay, but remember, the goal of the power grid is to adjust the generation capacity as per the demand fluctuations. Demand fluctuations means, suppose I am staying at home. Right now I am at home. So I impose certain load towards the grid. There are different industries. So this, what the load will be for a particular city or for the entire country per se, has to be supplied by the generating stations as a whole. I mean, by their combined strength, because it's a fully connected grid, so no problem with that. But then, how do we predict that? Okay, so if I ask you, even for a single individual, if I ask you how much energy you will be consuming tomorrow, we'll probably not be able to answer, because there are so many uncertainties corresponding to it. And I mean, there are huge amount of uncertainties. It depends on how much energy we'll consume. It will naturally depend on how much time I'm staying at home or at office. Also, accordingly, the total amount that I expend will vary. Okay, so if we can't do it for individuals like us, how can we actually predict what will be the total usage for an entire city or a locality or a city or for the entire country? But then that total supply which the generating companies have to, electric energy that they have to produce, has to be balanced by the demand. So this, I mean, this is very complicated. However, when we have millions of users which are connected to the same grid, these individual fluctuations, of course, to some extent, they get smoothened out, but they are, I mean, they can be predicted quite effectively if we take into account the different, like, for example, some holidays, some special extreme temperature, weather conditions and so forth. Okay, so more or less this can be predicted, and there are predictable peaks and troughs in the electrical, I mean, as far as the load is concerned. Now we have to design this power system in such a way that generation has to follow that load. So whatever we predict, so this prediction, I mean, this is one particular use case where AI is heavily used. So this, in this figure, it shows actually how AI applications are central to some of the things which I have already spoken of, in terms of as you can see here, I mean, we'll come across this term, what smart grids are, but then sector coupling, which basically says that if, I mean, there should be ways and means by which the the power grid would be able to understand that this section is having some imbalance in terms of the matching of generation and load, okay, supply and demand. So in that, so if such cases, so this increases oscillations, in the sense that the frequency at different parts of the grid becomes different. So it's like a synchronous machine. So oscillating at different frequencies make it very, very unreliable. Okay, it can break down at any moment. So AI can be used for sensing them and possibly partial isolating and so forth. Then of course we can use AI for monitoring the grid, in the sense that we can put different sensors all across the lengths and breadths of the the grid, the power grid all together, and then sense the data and use AI algorithms for checking whether the data which are being received are within acceptable limits or not, or they have some correlation with some previous cases where they are going into danger zone, in the sense that they are nearing any event or a fault. So this can be very basic algorithms can be written, designed for that purpose, and most importantly to maintain the maintain coordination across different maintenance works. This also makes the, you can say that it's very easy to estimate how much power will be generated by making it a sum across the, you can just sum up the different generation capacities of the different power supply units, the power generators as they are called. But then we have to understand that any device or any machine which is being used will have its own maintenance time. You have to maintain it also. Okay, so scheduling has to be done for maintenance. There will be breakdowns, sudden breakdowns, abrupt breakdowns. So all these things kept into, when taken into account, this makes this supply following the demand a very, very challenging task. So AI can be used. So some applications, similarly, at the consumption side, like for us, the consumers who use power. So at smart, there can be, not implemented so much in India, but the ideas are prevalent, in the sense that just like we have, for example, our this utility communication, this communication utility, telephone and so on. It's again a utility. Okay, so then in the market there are different players. So it's possible that we take our connections from different companies. So while doing that, consumers are supposed to make conscious choice which particular product he or she wants to buy. Okay, so different people might have conflicting expectations. Okay, so they as per their specific requirements, they want to take a plan or a connection which is more suited for their type of user. So similarly, that facility should also be, can be conceived to have in the, to have in a power grid, where the consumers can actually have a choice. For example, in India, the scenario is not like that, but in some small and medium-sized European countries, such a practice has actually happened, that the users can actually choose from which particular supplier at the distribution end they want to choose. So, and it's also possible using, the smart meters and all for that purpose. So basically, AI can be used for predicting and like automatically switching from one grid to the other. So for example, during the daytime, it can be found that one particular player is providing power at a much cheaper price, but during the late night hours, so it becomes costlier than somebody else. So the other, company or player in the market, so they, although at daytime they offer at a higher price, but then during off-peak hours when there is no load, so they can manage it better for whatever reasons. So it's, there are talks of doing something like this, a grid where your smart meter can intelligently pull power from different options and then pay accordingly. Okay, just to give you certain examples, a flavor of the different utility, the different applications of AI. Similarly, the AI, as I told you, is because it's a very commonly shared resource and a very critical resource. So everybody, all of us are consumers for this electricity. So because what we technically call as the deregulation of the power industry. So what has happened is that, and to bring fairness to all the different parties, to that generating companies and transmission companies and distribution companies are actually broken, I mean segregated out. It's not that a single player does all these three. So if that is the case, then because it's a very costly utility in terms of the assets which are required to run such a power system, so what happens is that there is a chance that it might have a monopoly. However, if you bring many players into the market, then it's also good for the customers. Like if you have many competitors, then there will always be competition, and customers will in fact get the, I mean, have to pay less because of this competition. A common sense thing. But then to do that, I mean, in electricity trading, so there has to be proper forecast channel, which are basically all AI applications. So based on the I mean the trend of usage of different patterns, based on the day of for which you are predicting. For example, today is Friday, a working day. Day after tomorrow will be a Sunday. So taking that into account, taking the weather conditions into account, okay, how much whether there will be ACs required at the different industries, offices, buildings, and so on and so forth. What will be the temperature if it is exceedingly hot, like sometimes at many places now in India the temperature goes beyond 40 degrees. So these extreme and sometimes during the very hot summers it rains, which gives us a lot of relief. We don't need the AC so much. So these slight variations also play a vital role in terms of those forecasts. So which again, different, I mean, AI in its different forms are actually employed for that. And there are naturally, as I told you, this trading happens. Okay, the trading happens, for example, in the sense that one enterprise within the power industry so wants to purchase something. So for example, there are different grids. I mean different, what do you call that, subsection of the Indian power grid only. So they will have, let us say, 5 different generating stations. Okay, and also they will have the loads in the sense that some 4 or 3 or 2 cities within that. So now at certain points in time during the daytime and so forth, so the consumption might be such that the local capacity of the local generators might not be sufficient. So they will have to trade it, buy the power from some other player in the market. And then at night time also, it is not necessarily that the generation stops completely. So they can trade it back. I mean, so in that way, the very, very complex mechanisms for trading and all has to be there in place, which actually happens. And also to monitor the type of trade. So AI is also used for continuously monitoring that how much power is being fed to the different stakeholders. For example, smaller countries like in our neighborhood, in our vicinity, like Nepal and Bangladesh, they consume a lot of power. So it's not manually possible to keep track of how much power is being given there. So, and there are, AI can be used, AI in fact is used very, very commonly for such purposes. Okay, so what is AI? To put it, and just I have to do it because we have been, I'll not focus much because the entire week I'm sure all of you have been have gone through the in rigors of this, what AI is. But basically speaking, very simply put it there, we try to have machines which are intelligent, so which can work and react in a more human sort of a way. Okay, so why it is important in the power industry? As I told you, the power industry is a very, very complex system. So the interactions of different components of the system are very, very complex. There are so many substations, so many transmission lines. So if it's not possible that if you put some human beings for doing the monitoring and control, they'll be able to keep track of the huge volume of data. Excuse me. So machines can do this part better. Machines can read and very, very reliably reproduce data. Once you write an algorithm, they can very reliably reproduce the results also, and very perfectly, unlike human beings. Okay, so over the last 2 decades or so, there has been, just a minute, just let me have some water. Sorry. So over the last 2 decades or so, there has been a lot of advancements in terms of how we have how the state of the art in terms of artificial intelligence has increased. Many reasons, primary to all the reasons, is the amount of computation powers that has been at our fingertips. Okay, so the computational capabilities have increased by leaps and bounds. Okay, so for example, for now, whatever we get as PCs or small workstations are actually thousands of times powerful than a mainframe computer that we used to have in the 30-40 years back. Okay, so that is the power that we have got. So this has in fact enabled us to think of more, I mean, to develop algorithms which are much more, which are capable of crunching more amount of data. And there has been lots of advancements in the sensor technology. So basically, what we say is that these are all ICT enabled, I mean, information and communication technology advancements, which has brought us to this point where we can do all this humongous amount of computing, and then it comes in different flavors, of course. Okay, deep learning, and there are different forms of this machine learnings. Okay, reinforcement learning and so forth. So these have come up. So all these techniques can be used very efficiently for making a power sector which is which can be treated as a smart. I mean, so that is what we call it, a futuristic power grid. The name we use very commonly is a smart grid. It's a term which has very deep implications. Okay, so for the purpose of just putting it, I'll just tell in principle what it is, but to get a comprehensive result, I mean, definition of it, of course, we have to, I mean, take into account through some standard definitions which are given by IEEE and so forth. Okay, so what it says, a smart power grid, what is it entails is basically having sensors across the different different components of such a grid, which we have, for which we have already discussed. So an interconnection between our residential homes, and for example, in case of a city like setup where we have different residences, different shopping complexes, or shopping malls and so forth. Okay, and we have the different offices, the different factories. Okay, so this part is I mean, this part marked in this pink. So this basically shows the load side of it, and of course there are a lot of emphasis which goes on currently to avoid this petrol and diesel. So vehicles and all has to, I mean, are moving towards using electricity driven. Okay, so which are clean in the sense that they don't emit carbon dioxide. Okay, and on the other hand, we have the generation side of it. So different varieties of it. We have thermal power plants, and then small isolated, not isolated, I mean small scale power plants, so of various descripts, and then with different hydraulic power. It's not hydraulic, rather it should have been hydroelectric, which basically means that we use water resources at different points for generating power. So basically electricity is a electromagnetic wave at the end of the day. So it can be this form of energy can be transformed from different forms. So it can be through burning of coal and so on and so forth. Okay, by I mean the kinetic energy of using kinetic energy of water, that can be transformed. So different ways can be just, we can use, I mean, use solar panels for different renewable purposes. So this is solar, and similarly wind energy can be done. So a smart grid connects these two extremities, where we have here the load side and we have the generation side, and ultimately, as we have already told, the generation should always follow the load. Okay, so this part keeps on changing, and a grid, a power grid, and which interconnects all these different components, has to make sure that it generates optimally. So you might think that it's very easy to, I mean, because we have actually very excellent technologies for monitoring what is going on. Okay, I mean, timestamp based, GPS enabled, different scenarios are there, I mean, it's possible to get all the different data, but then even if you know data means in terms of load, I'm saying how the loads are fluctuating, that can be monitored at real time. But then at the generation end, all these different machines which generate power, they have a lot of what we call as inertia. So although we know how much power is actually, I mean, what is the actual load at any instant of time and how it is changing with time, even if we can monitor that, but then these machines actually takes a lot of time when they are generating, when you want those same machines, those same generators to increase their generation capacity. It's not like switching on I mean, plugging in a switch and putting it on or off. It doesn't happen like that. Okay, particularly for thermal and hydroelectric power sources. So they take sometimes hours together to, I mean, increase their capacity from, let us say, 80% to 85 or 90%. Sometimes even days together. Okay, so following the, I mean, load and generation is practically an impossible job. So then what this smart grid can do, this grid is called smart grid because it has some amount, I mean, huge amount of processing capacities at different, distributed across all this infrastructure, of course, by which it can keep on processing how the, it gets a very good idea, fairly transparent idea of what is happening with the data at different load points, different generation points. And then by keeping track of it, it has certain algorithms to actually maintain that balance. For example, if the load is, if the generation is falling very, very short, then probably it will identify areas which, if isolated from the grid, if they're taken apart from the grid, then possibly the supply-demand equation can be balanced. Okay, so intelligently cutting off the different parts, and also there such proposals can be there. I mean, we can have algorithms which can suggest something like that, and then there has to be proper actuation also at the substation level. Okay, so such a scenario makes it the power grid, electric power grids, smart. So these are all works in progress. Currently, in the Indian scenario, of course, what we are seeing is that the monitoring part with SCADA, and also the recently there has been a lot of investments in 2012, 2013 with certain pilot projects for synchrophaser data synchrophaser data monitoring. So there has been a lot of PMU and all different sensors, very fast, very efficient, but then the control part of the grid is actually not fully operational. In fact, there is very little work which has been done for automatic decision making using that data. Okay, so that we can see later on. Different techniques, not just exclusively AI for decision making, but the sensors which brings all this data. So this IoT and its allied technologies, like whatever ICT technologies I was telling. So basically ICT technology, this term information and communication technology actually captures everything. Okay, it captures the processing required for making decisions using the different AI intelligence algorithms and so forth, and also the communication, different protocols and all which are involved for, for the different sensors to communicate. Okay, where the different, not just devices feed data to a network, but in fact where different devices, there are protocols which are actually there for the devices to talk to each other. Okay, using the common term we use is M2M communication. Okay, so basically built on information portability. Okay, so this power sector requires all this combination of different digital innovations. And as we'll see towards the end of this session, that although ICT technologies opens up a lot of scope for the power, the power grid, to make it smart, to make it sustainable, which makes it sustainable growth is always the goal. Also, although it helps in a big way, however, there would be, naturally, every solution comes with its own set of issues. So one possibility is that if we connect all the systems with so many sensors and I mean, then actually if that data is compromised somehow or the other, so that brings us to a point where the entire grid's security and its operation becomes a threat, provided if we have certain security vulnerabilities. Okay, so that to take care of that, a lot of recent focus has been to develop secure mechanisms which can in fact prevent any unauthorized access or unauthorized I mean, what do you call that, writing to the entire database systems. So I mean, to prohibit them for such unauthorized accesses, let us put it that way. So blockchain technologies has been seen as a very prominent prominent technology. So all these together, a combination of such digital innovations actually are required for making the smart grid intelligent, as is the goal. Okay, so in the Indian context specifically, as I have already mentioned, the different European organizations have actually come a long way in terms of how they are seeing their grid, how they are inculcating smartness in a gradual process. So this has not been the case with different. I mean, in the Indian scenario, although we have the largest grid and probably one of the most what do you call that? One of the most complex grids in terms of the variation of the supply and demand. So in places like Northeast and all, where there are a lot of water resources and which are remotely located, so we can generate a lot, but they don't have local loads because there are not much big cities. And on the other hand, at places like Delhi and Mumbai and all these, so it's very difficult to have huge power plants there because of I mean, you can't have a power plant right in between a city. Okay, so because there can be potential dangers of it also, pollution and all, so many other factors to be taken care of. So it's a very, very complex scenario. So as I told you, like most of the emerging economies, like in the African nations and the ASEAN and the South Asian countries, so the use of smart grids in these countries actually lags in terms of, I mean, vis-a-vis, if you compare it directly with the other advanced economies, particularly in Europe and the US, so they lag. Okay. Of course, not to say that none of these developing economies have not worked. China has, of course, if you say it's in the Southeast Asian countries, but then they have a lot of infrastructure in place. But then Brazil, the Gulf Consortium, the Malaysia, South Africa, Thailand, Vietnam, they are actually progressing at a pace which is much better. India, of course, has through different programs by the federal government of India, like the Digital India, the smart cities. We are, I mean, in the process of identifying key areas and providing, I mean, to achieve this goal of energy security. Okay, where, I mean, we can depend, there should be a security of how much energy, at least minimally, how much we get currently. What we are hearing that the rural electrification is going on at a very high pace, particularly in certain areas. Okay, of course, so there has been initiatives, but then it requires a lot more. Okay, and then one very prominent challenge which comes in the, I mean, which obstructs the path of this revolution in India is, of course, not just in India and across the world, is this climate change thing. Okay, so for example, you might think that particularly for hydroelectric projects, no, so what is the resource, the primary resource in case of hydroelectric power plant is to have uninterrupted supply of water, which might not be a very big issue, I mean, on its own. But then because of climate changes, no, so the patterns of the rainy seasons and these things have actually, I mean, they are actually departing from their standard variation. So it has become more challenging to plan for that. Okay, so there are challenges in the path ahead of us. So now I'll move a bit quickly before I move to a specific example. Then that we'll see. So then don't have to. I mean, this is a, I mean, continuous cycle to have sustained growth of this particular industry, or for that matter, any modern society. So it needs a sustained growth has to be sustained, keeping electricity as the key pillar. Okay, so the utility network needs to be transformed. For example, I mean, to transform the energy, the many of the assets that we have, I mean, for this what do you call it, we don't call it transmission lines. Okay, these transmission lines, so these assets were being built from the 70s and 80s and 90s also. So now the requirements have changed. So to transform this utility network needs an upgrade. Similarly, the performance of generation has to be improved, and of course the efficiency of energy. So it's not that whatever you produce can, I mean, you directly you can mirror it and have it at the load side. So it doesn't happen. Every system we know is associated with losses, which is very, very prominent for electric grid. So there has to be a lot of improvements which has to be done for having more efficient energy. For example, I mean, this has to happen all across the different devices or components of the electric grid. What we are experiencing right now, I'm sure most of us will be able to appreciate that the amount of transformation we have in terms of our lighting loads, okay, at our homes. Okay, previously we used to have those filament bulbs and all, so they used to be 100 watts, 200 watts, and still the amount of illumination we used to get out of it was much. I mean, compared to now what we have with these LED bulbs and so forth. So, I mean, compared to if you compare a 100-watt filament bulb, the amount of light it gives, and the 12-watt LED light, what it gives, the amount of, in terms of the illumination, which is the purpose of lighting after all. So this is something which we are calling efficiency. Okay, so that efficiency has to be there at all levels of the grid, be it at the distribution end at our homes or be it at the generation end. Okay, here, so improve the generation performance. That is, these are continuous processes. This cycle has to keep on going, and then we have to transform the customer operations. Okay, for example, as the grid becomes more and more complex, and we are, I mean, the grid operators are in fact gradually understanding that it is very important that the main stakeholder in the entire cycle of operations are the customers. So if they can be somehow involved in grid operations, like if the customers are given an alternative. Okay, we don't have right now in India, but certain countries are doing it. For example, customers can also be, because they are the main stakeholders for the entire grid, because then customers are everything. So now if the customers can be involved in the process of proper energy usage. Okay, like suppose, I mean, usually power generation always lacks the demand. So now if somehow in the households, for example, if we can involve the customers and give them some incentive to change their pattern of energy use, they will probably not use the in the household, they will not use the heavy loaded things, like, for example, let us say one example, the what do you call that, washing machines. Okay, so they consume, they are quite heavy machines in the sense that the load is quite something for washing machine. So however, it does not matter whether the washing machine operates in the daytime or at night. Usually we do it during the daytime because it's convenient. But if we can somehow have a scenario where we involve the customers, because see, the main challenge is that if there is a generation capacity for a particular generator, let us say 100 units, whatever, megawatt, kilowatt, whatever, operating that plant at 100 megawatt, gigawatt, whatever, 100 units is really a challenge. It costs very much. Would ideally operate it at 80%, 90%, somewhere in between. Okay, for efficient use. But then if we can encourage the customers, so to do works like that, which are not very essential. So if we can ask them to change their pattern, then the daytime load can be shaved off a bit. Okay, so that actually is like a way in which the customer operations can be transformed, right? So if they are also involved, that would lead to better, smooth operations of the grid, and of course a continuous improvement in terms of operation excellence has to be there. So most of the algorithms which are there, AI algorithms which are there, so they are and they assume a lot of the things. With a specific example, we can discuss it later on also. But then as the nature, as the grid runs on, as those algorithms keeps on running over a period of time, they will self-correct themselves. Okay, so continuously improvement of this operation excellences also has to be there for having sustained growth in this industry. Okay, if there are any questions or any comments at this point in time, particularly if you want me to discuss any specific examples, please let me know for a minute or two. Otherwise, please do let me know. Just a minute, I'll just pause for a few minutes or so.
Any of the professors, like participants, having any query or like interaction?
You can use the chat box. That would be
yeah, sure. In the meanwhile, also you may put into the chat box. Don't wait for the last moment.
Yeah. So next more 20-25 minutes, I will speak. Then I will stop and see if there are questions. Please do let me know.
Sure.
Okay. So now based on this discussion, actually, we'll now see that, although we have been discussing about the different AI techniques, the different, some of the use cases, what I have to a very simplistic way, I have discussed it, but it also involves to have, to make it possible for such algorithms to run. What we do not appreciate, because it's always prevalent in modern days infrastructure, is that we don't appreciate that we need very specific techniques for managing the data. Okay, so with so many sensors all across the grid, at least for the Indian grid, this huge amount of assets, most of them being equipped with certain sensors, the amount of network traffic it creates, the question of having all those data to a centralized server, getting them within acceptable time limits for real-time processing is a big task. So it requires very specific data handling techniques also, which we technically call as big data techniques. So they, actually we use a lot of these techniques. Okay, what we definitely use, what all utilities has to use, is it's not possible for all this data to hold on a centralized server. So that is not attempted at all, because the system itself is a completely distributed system. So all the data are stored at different locations, and there are actually schemes, particularly like the map reduce techniques and so forth, where instead of moving the data across the different data centers, which makes it very slow, unreliable, data losses. So instead of that, using certain those programming paradigms, okay, particularly the capacity of invoking certain methods remotely, some procedures, okay, remote procedure calls and so forth, which the programming languages like Java and all can do. So it allows data to reside at their own places, but then using different techniques like MapReduce and all, moving the computation from one place to the other, because the size is very less, so they don't account for a lot of network traffic too. Okay, so a lot of techniques are there, so which we don't particularly when we write programs and all, which we do not appreciate it very much, because such big data techniques are so ubiquitous in analytics, we tend to forget it, but they do play a lot of role. Apart from MapReduce, of course, what is coming up is the in-memory computation part of it. Okay, so if you have any discussions on that we can discuss later on also. So any energy management software of any scale as of now, modern days, so they use all these, they leverage all these existing big data technologies. Fine. So then there are a lot of use cases. I don't know how much we'll be able to discuss it. One or two I should show what. Yeah, a few AI applications. Let me focus. One is, of course, the fault prediction. Okay, so fault prediction. Are there any questions or what, from where I am getting all these sounds? Okay. Okay, so we'll discuss just a few prominent AI applications. I don't know how much I'll be able to do that. Okay, let us give it a try. So fault prediction has been one of the major applications of where AI is applied in the energy sector, of course. Okay, so along with real-time maintenance and identification of like ideal maintenance schedules. So in an industry where equipment failure is very common, we have to remember that these equipments in the parts, I mean, different substations and at the different generating stations, they operate for years together, tens of years together, 20 years, 30 years, 50 years. So I mean, a failure there in different components is not a very rare occurrence. It's a very common thing. So in an industry where equipment failure is very common with potentially significant consequences, so AI with appropriate sensors can be very useful for monitoring the equipment. Okay, because if you can somehow, with using certain AI techniques, can be able to predict which particular machine component is about to fail, so we can schedule a maintenance for that particular component, get it repaired. So if that can be done, actually it saves a lot of time and energy for the grid, because if the machine fails, then the subsequent recovery takes a much larger time than a scheduled maintenance which can be planned. So predicting such faults is a big bonus. Okay, bonus. It saves resources, it saves money, it saves time for all the people. Then maintenance, a lot of maintenance things are actually facilitated by image processing nowadays, as it is mentioned. For example, I mean, I think it's in UK. So in the English National Grid, I think they call it something, the name is there. So they are, I mean, actually using drones to monitor the different wires and the different pylons that transmit electricity from the power stations to the different homes or to the different distribution ends. Okay, so equipped with such high resolution, they have still cameras, they have infrared cameras. So these drones are particularly useful in fault detection. There can be, I mean, there had been attempts previously to do it with fixed cameras, which keeps on looking at those lines and then try to predict. But then, I mean, for a larger, think of a larger transmission and distribution capacity. So it requires a lot of cameras, and these cameras, which can, based on the images, if you want to do prediction, they have to be very costly cameras. So if you have a few drones, first of all, the drones can cover a lot of space. And for example, if I'm not wrong, they were using more than 7,000 miles. One drone could actually be able to monitor in a day 7,000 miles worth of, more than that actually, worth of transmission lines. So basically the entire infrastructure for a small country like UK. Okay, so what happens? These drones will keep on capturing the data, but then we need AI. So the images are not sufficient. You can't ask a human operator to sit and keep on following, I mean, visually the patterns at the different transmission lines and then predict. So it will never be perfect, even if it's a very efficient operator. But then as human beings, they will have their own frailties in terms of, for example, we don't have the same mood every day. It's possible that we are human, so we might have a good fight at home before we go to our office, and then we'll naturally make mistakes, we'll not be able to concentrate. So it happens all the time. So AI algorithms can be used very efficiently. Okay, so it saves life, as we discussed previously. It saves time, it makes everybody's ambience more comfortable. Then energy efficiency and related decision making. Okay, so we are actually now using a number of smart devices, such as you know, Amazon is having that, what is called Alexa, Google Home. Nest we don't use so much. Okay, so this enables customers like us to interact with the different devices that we have in an IoT setup. So this digital transform within the home and its corresponding energy management, and where the different devices, the appliances which are connected to that particular home, can actually use AI to optimize the energy consumption. Okay, so most modern day TVs, even they are not so-called smart devices and so forth, but they can auto adjust in the sense that you don't have to explicitly switch it off. Okay, it happens with our mobile phone screens and so forth. Similarly, many devices are also coming up which are having such facilities, but there are explicit examples. Like if you have a home energy, what do you call that? This like a Google Home and so forth. Apply, a controller for all the home devices, and it's possible that AI can be used for based on what patterns it sees, and accordingly take a decision when to switch on or switch off. So it adds to the energy efficiency and reduces the energy consumption at home. Okay, and as it's obvious that with population growth, urbanization in low income countries like ours, so what has been happening, and I'm sure you will be able to appreciate that the cities are expanding. So AI can be used very effectively to understand this rate of growth, and accordingly, if you can understand the growth with certain data which AI can actually produce, so we can actually plan for the expansion of the cities better, which unfortunately in India is not being done properly. In not just in India, in most middle and low income countries, that is the case. Okay, then AI can help improve the forecast of the electricity demand. Okay, because as I told you right at the beginning, that the key goal for a grid which is big is to match this supply and demand equation. Okay, so AI can be used to refine the already existing models, and if you can somehow or the other able to do better forecasts, that naturally improves the production. Okay, so this is particularly important in the transition towards renewable. So what what the modern society, particularly in the first world countries, what they are trying is to have certain renewable sources of energy right at every homes and offices. Okay, so they can avoid because more the energy they consume from from anywhere from the grid, at somewhere or the other some natural resources have to be expended towards that. So to avoid that, it's possible somehow or the other, if you can generate the renewable energy at their own at the premise itself, so that is sufficient, and whatever energy requirement it falls short of, that can be taken from the grid. And it's possible using AI to actually see if at the residence, if the energy which is being generated by the renewable infrastructure which is there at the home, if that is more than what is being expended at home, so you can supply it to the grid and then get a discount on your bill and something like that. So AI can actually do this type of things also. So AI-based forecasts combined with energy storage infrastructure can reduce the need to have a backup system, like we used to have diesel DG sets and so forth. Okay, so these are like some cases where energy efficiency and decision making are involved. AI can help. Then disaster recovery, of course. So I don't know whether you're aware of it, but then in the US in 2017, I forgot where it took place. So there were, some hurricane struck, and it was like the entire infrastructure went off. So it took only 10 days to recover from it. Okay, whereas in the, I think 2 or 3 years back, when a similar hurricane occurred, so that to have the infrastructure back, so it took, it used to take a month or so. What was our case? Unfortunately, in 2013, I think, when filing came, I was in Berhampur. So it took more than a month actually to get the electricity infrastructure back. So with AI systems can improve the assessment of the damages. So just by a self-test mechanism, it is possible to check which parts of the power grid are still connected, which are not. So such type of disaster management, there are enterprises which specifically focus on such disaster management cases. Okay, how they can optimally, in a very short amount of time, predict which infrastructure has to be rebuilt first, and so on and so forth. Okay, then the prevention, I think, prevention of losses due to informal connections. So losses due to informal connections is a very, very important challenge for the power sector. So here also AI could be used to spot the discrepancies in usage patterns. Okay, for example, many times it happens that particularly we don't have it here, but it's possible that I'm sure you'll be able to appreciate. Previously it was being done many times now. People tap into power, and then draw power from the electric distribution lines. Okay, so AI can help in assessing any such flow of power, unregulated. Okay, informal. This is what has been referred to as informal connections. Okay, so in a locality, the individual meters can be connected as smart grid equipped with the smart meters at different homes of that particular locality. Will very easily give you the total amount of energy which has been expended by the sum of all the different houses, and then there will be meters at the distribution end, which can very easily find whether the sum of all the residential usages is is less than whatever, or less than or equal to the total power which has been consumed. So if there is a discrepancy, this can very easily be tracked. Okay, so also similarly, there can be other non-technical, vast number of different non-technical reasons which also add to the losses. So AI algorithms can actually be implemented for such purposes also. Okay, so that's about it. Just I wanted to show a bit of what we have been doing. So very briefly, I will do that. Okay, just in just maybe 10 minutes or so, I will just tell to see what this is actually a core research grant project which I had, for which I have been funded by SERB. So here, as you can say, just philosophically, I'll brief you. So what we were doing is that we had suggested with POSOCO, the power grid, the subsidiary company, which is responsible for operation. Okay, operation and control, I think. POSOCO, power system operation and control. Okay, so they had all these different sensors. These sensors called synchrophaser. Synchrophaser is the general name, and they are called PMUs, the phasor measurement units. So they are very, very costly sensors, but they are able to track the voltage and the current which are flowing across a bus, electric bus, at a very high resolution, at a very high frequency. So we get 25 samples in 1 second. Okay, and I think in India the plan was to have something, we don't have it here, something around in a pilot project which went across for having all these different PMU sensors across the Indian power grid. So they estimated of around 1700 to 2000 PMU sensors which would be required. So in its full capability, it will actually be able to replace, if not augment the capacity of the existing SCADA EMS things. Okay, SCADA EMS is the current breed of this thing based on which POSOCO does all its control operations. Okay, so I'll not go into it. So this actually shows you, I can't expand it any further. So the software was of course purchased by some US firm, from a US firm, I think Scavenger Engineering Labs or something, ACL. So they had a PDC. PDC stands for basically the data concentrator. So all these PMUs connected to the buses. So they are connected to a PDC. The PDC is where the sort of the data repository. So, and then based on the data which are, which comes from all these PMUs, so they are stored in a central, through the PDC, they are stored at different location wise, at different, their corresponding LDCs. I mean, the Indian power grid technically is divided into 5 regions: the north, west, south, and east, and the northeast, of course. So with these 5 grids, regional things. So regionally they are collected, and then finally there is a national load dispatch center, LDC. So where all these algorithms were supposed to run, and then control action were to be changed. However, it's not a working system. The PMUs just are able to monitor it. So we had actually proposed to use, once we get all this data, which was, agreed by a MOU, that POSOCO and Power Grid will actually allow us to get this data. So we had proposed also an architecture how to engineer such a scenario where we could artificially actually make a test bed, because it's not possible. It's very sensitive data. You can understand, because if the Power Grid's current data is somehow gets public, then actually anybody can use it for improper purposes, for creating a lot of disruption in the entire power system. So it's not freely available, neither with the thing. So we got actually some previous data a few months back. So that data, with, of course, there was a MOU which was done with our institute in IIT Meghalaya and the NER Northeastern Load Dispatch Center in Shillong. So then we had what we are in the process of doing, almost done, is to have a setup where we could actually artificially throw the different data which are received from different PMUs. So we could stream it, and then we have a Hadoop distributed storage, and at the different PMU level, so we could actually emulate this thing. Okay, so we had a distributed storage, and then we created the zonal PDCs. Zonal PDCs, like as I told you, zones represent the 5 different locations. So we could do something like that, not to a full scale. Okay, so this was our goal, to analyze the disturbances. And then in order to do that, we, as discussed here, we already had the Hadoop distributed storage in place. We implemented that, and we also, for doing this emulation purposes, we used the real-time data analysis using Apache Spark, which is again open source. And then we were having the historical data which was being pushed, and then as we ultimately did some classification of the different events. Okay, so that model, of course, is a evolving model. It's because what we did was because getting data is not easy, frankly speaking. So it's very difficult to get data from there. So we had very limited amount of data, but we were able to throw all this data, emulate the scenario where all the connected PMUs could actually work at the same resolution, where they were sending the 25 Mbps, 25 samples per second to the PDC. Okay, and everything was, all these different data from the different PMUs. So they were accumulated in a historian. Historian means we used a workstation for this purpose. So at the substation level, and we had a central PDC. This architecture was proposed in analogy to the way POSOCO actually has their organizational structure. So there are the individual substation level PMUs, and then there are the different PDCs, the substation and central level PDCs, and finally what is there at the NLDC level. And then we were keeping on updating this for the real-time analysis. So we were getting a copy, we are able to throw a copy here to Spark, and then we are also updating the Apache, Hadoop storage there with whatever, whatever new functionalities for classifications were being, whichever data trends were identified. So they were also being fed to the, and as well as new analytic rules were being framed and are being framed, and they are actually being stored. Okay, and then for certain cases at the Spark level, so it was able to identify certain anomalies in terms of the amount of, the fluctuations of voltage and currents. So these models are not very effective, but we could actually make a working prototype of it. With more amount of data at our disposal, we'll be able to make a much more reliable analytics. So we are in the process of handing it over to Power Grid. Probably by October, we'll be able to do that. So the pre-processing and all, we cannot actually, we take a lot of time. So some sample algorithms and the Hadoop implementations were shown, because this was developed, this PPT in fact was developed as a part of our annual progress that we had shown to the Power Grid. So this is one specific case which which we at NIT Meghalaya, in collaboration with the Northeastern LDC at Shillong of Posoto. So we are in the process of contributing actually. Okay, so this, of course, as I told you, there will be, okay, we'll not go into it. This study is a case which was done in Brazil actually for identifying power thefts. Okay, like even in India, it is common in some states actually, people tap into the power distribution lines and pull out energy. So in an unauthorized manner. So anyway, so the future of power sector will be more and more open to the application of AI, of course. Okay, for a number of reasons. First of all, AI companies. I mean, there are. I mean, challenges also. Okay, so AI will be involved more and more in the power industry. However, one of the primary challenges, like people like us and those who are involved in applying AI, is the fact that although AI, I mean, there are a lot of expertise in maths and computer science, but most of them actually, in fact, are not aware of the actual way the power system is engineered for its operations. Okay, so this is a big problem because but the potential of AI application, applying AI in the power sector is, I mean, at different levels it can be done. However, there has to be it is a great need to educate people like us, those who are all, as computer scientists, we are involved in applying that. So deeper aspects of power system should be actually known by us, and we should be able to know it accordingly. For example, to put an example in point, we can think of all the different cloud-based applications. So they are very widespread, and there are so many cloud-based tools, right, for doing for ready-made AI applications, for providing ready-made AI solutions. But there are many regulatory restrictions which actually prohibits the power system operators like POSOCO and all to apply these existing tools. Okay, so this of course has been changing, and I'm sure the government of India has also come up with certain regulations how, for certain data, not for all, which can be because of the security concerns, so which can be loaded in the cloud and all. But usually power companies, they're very hesitant for releasing their data, storing it at the cloud, or using cloud-based tools for analyzing their data. Okay, then so that is one case. Then the reliance of cellular technology also limits the AI's potential, particularly in rural and other undeserved areas. Okay, then the digital transformation of the power grid has made it a target for attackers. Okay, so that is a very along with every facility comes a wider responsibility. So as we open the power system and all its data for being used by artificial intelligence, so we also open the possibility of hackers to intrude into the system and then carry out their agenda. So there has been such disruptions. Okay, this Ukraine 2015 here mentioned here is a very alarming example, and this plot shows the number of vulnerabilities, cyber vulnerabilities which were attempted. So from this 2000, practically only a few, less than 10, 2, 5, 10 like that. And since the last 10 years, so the rise in the number of cases has been very significant. This of course, the source is based on something on 2015. At the end of the slides, I do have an acknowledgement for this particular source. Okay, then integrating the different data sources are also challenging. Then most importantly, one of the, which I can appreciate personally, one of the main challenges in applying AI for future power grids is the fact that AI-based models are essentially, at least the way we use it, is like a black box. Okay, so to the majority of the users, we don't understand how they work. So because we do not understand the inner workings, or we do not know actually how they were developed, so this also brings us to a security risk, in the sense that the existing models are far from perfect. Okay, had the existing models been perfect, the situation would have been different. But because suppose if I develop a model, which I'm doing currently, so I will have very limited amount of data for whatever regulatory problems or whatever, very limited amount of data at my disposal. So I will test my model and then claim that this is sufficient. But if I give it to Power Grid and Power Grid in turn uses it, then and the people who will be using it will not be aware at all of how this was developed and how it works. So they'll be treating it as a black box. So what it entails is that in due course of time, I mean, because from my side it was not tested thoroughly for different data ranges, so it can create huge losses. Okay, so when these two are combined, what is combined? Like better analytics, better sensing, better, I mean, breadth of data across it. I mean, across all the different devices, the different sensors, then AI can be used for automation of simple tasks. Okay, to do it using human beings is a very challenging. So that problem can actually be solved. And finally, I think, yeah. So finally, there has been an imbalance in the priorities also for most of the organizations which are involved in it. So there has been a lot of attention given at the distribution side to implement smart sensors, and I'm talking of the European countries. But then these tools has to be actually equipped. I mean, they should be designed with a focus on the main stakeholders, the customers. Okay, so from the utility side, there should be a lot of emphasis, more prioritization of designing things at the transmission side. Okay, so these things are lacking. So we have discussed from the beginning, we have seen that how AI can help, what are the different use cases. We have taken one specific PMU data management scheme, which we are currently doing it in NIT Meghalaya, and finally pointed out a few of the challenges that are there, which are there for making AI a part of, integrated part of modern power systems. Okay, so these are basically the two references from which I have taken most of the things. If there are any questions, please do let me know. We'll have a discussion.
Any question from the participant end? Any question from the participant? Roju sir is want to ask something. Roju sir.
Yeah.
Sir, namaskar, sir.
Namaskar. How are you?
Yeah, fine, boss. What about you?
I'm okay. I'm good.
Great. Sir, as you have a very good delivery of something about AI and it's related to power sector. If possible, kindly enlighten us about the, the project funding, how bigger number of openings are going on, but it's not possible for us to triggering the right one. So as you have a very good vast experience related to projects, so if possible, just kindly enlighten us in which sector we will address, so that there will be chance for being a beginners to attract the grant organizations.
This meeting is being recorded, so offline I can tell you what actually happens. But then one rule of thumb can be you actually try for something, attack a problem which is easy to solve. So that means you take up an area where, for writing a project which is very new, and which there are some government schemes. Okay, so for example, if you say, just because government comes up with certain policies, the Niti Aayog and all, like for example 5G is one of the key thrust areas. So if you decide to write a project, it's not that you can't write on other, there are hundreds and thousands of projects being funded from other areas also. But then we, from our perspective, from the way you ask the question is, because writing a project is like shooting at certain unknown parameters. So we are talking of the probability of making a hit. So if you do it with some, if you focus your projects towards some of the government initiatives, I think it makes it a bit easier. It's something like a Monte Carlo simulation. You keep on hitting it, and then based on that, what data you get at the end of it. So I think that will improve the probability. But then you have to have an expertise in that area. So that should also mean that you keep on writing papers in that particular area. Otherwise, they will simply reject it, saying that the investigator does not have a profile which matches this area. So
Okay.
we said,
Thank you, sir.
this meeting is being recorded. This meeting is being recorded. I cannot tell you other detailed trade secrets.
Sure, sir. In offline, I will discuss with you.
Recently, I think last month I got one more project worth 50 lakhs. That was from the Ministry of Electronics and IT. That was a 5G related project. So that's why I'm saying 5G is there in the national agenda by the government. So even if I don't know much, but if I try, usually it pays off. And this project which I'm having with SERB, which I'm doing with Power Grid, so that at that time there was a pilot project by the Ministry of Power actually for having all these sensors. So what will they do with sensors if they don't have a scheme for analyzing the data? So the second reference which I have given is that particular thing. You can see from the name, investigation on data-driven event detection schemes using Indian Power Grid synchrophasor data. So it's very specific. I'll be using data from those sensors and I'll do some analytics. So this was awarded as a core research grant. So you have to be a bit picky and choosy where to apply. We can discuss it later.
Yeah, thank you, sir. Participants, if you have any questions for Professor Sinha Roy, you may ask to him. Otherwise, you may share it in the chat box so that we can pass it to you.
Sir, thank you very much for sharing the wonderful knowledge and wonderful ideas to all the participants. It's really very, very helpful to all the participants to do the future research, and also artificial intelligence is one of the concepts that is very, very useful nowadays, and the future is also very bright. Okay, so thank you once again, sir, for giving us the time to take some knowledge from you. Because I sent number of mails, then after that I received the confirmation.
No, usually I respond to mails in a very short turnaround time. Unless if I don't respond, probably I have missed the mail.
Okay, sir. Thank you, sir. Sir, it's a kind request to all the participants, kindly on your camera.
Oh, photo session.
Yes, sir. All the participants, kindly on your camera.
DIptendu sir already heads us. Sanjay sir is already joined in this meeting. Sanjay Kumar sir.
Yeah, sir. Good evening. Namaskar.
Thank you very much. Namaste, sir.
Professor Agarwal, please switch on your video.
No, it's okay.
We have to walk the talk ourselves. Thank you. Okay.
Now I think it's okay. Thank you, sir, for accepting our request. Namaste, sir.
Thank you. Welcome.
Namaste, sir.
It's a pleasure.
So we have the validity sessions after 5 minutes. Sharp 5:05. We are going to start our